A common experiment in introductory chemistry classes is to place a piece of aluminum into a blue-colored solution of copper 2 chloride. Almost right away, brown-colored powder is formed on the aluminum. In short order, bubbles of gas begin to form on the surface of the aluminum as well. As time goes on, the brown precipitate gathers on the bottom of the beaker and the blue color of the solution fades away completely. The opposite effect is observed when copper wire is placed into a solution of silver nitrate. Silvery crystals grow on the wire as the solution turns a distinct blue color. However, if a piece of copper is placed into a solution containing aluminum ions, or a piece of silver is placed into a solution containing copper ions, there's no reaction at all. These experiments are used to introduce the activity series of metals. Quite simply, the activity series ranks how reactive metals are in relation to each other. These reactions are called single replacement reactions for a good reason. The copper replaces the silver in this particular example, and aluminum replaces the copper in solution in this example. Because aluminum is a pretty reactive metal, under these conditions it also reacts with water a little bit, and that's why you get the hydrogen gas. Looking at the activity series, if a metal appears higher on the list, that is, a more reactive metal, then it will prefer to lose its electrons, and the less reactive metal, which is already in solution, will take up those electrons and precipitate out as the metal, usually. Like everything in chemistry, there are more exceptions to the rule than examples, but more on that later. According to the activity series, metals from sodium up will react with water. Magnesium and aluminum can react with water too, but not spontaneously. Other conditions must be met to get those reactions to go because of the natural oxide layer that covers those two metals. In a previous video, I reacted sodium with water and lost a beaker in the process. Many years ago, I started exploring ways to make that reaction even more spectacular, as if it needed to be, by exploiting the differences in reactivity predicted by the activity series of metals. My intention was to explore that again when I made the video on sodium, but it was the middle of winter, and you've already seen why I didn't want to do this experiment in the house. Sodium is right near the top of the list, and it's the most reactive metal I have in stock. Remember that a more reactive metal precipitates out the less reactive metal. I wondered if I could add some lithium metal to a solution of potassium chloride, precipitate out the potassium, and have both the lithium and potassium reacting with water. How insane would that be? That's the mad scientist in me. But the professional chemist says I need to do some experiments first. So here's what happens when sodium and water meet. The sodium loses its electron, which is to say it's oxidized. Remember that water exists in an equilibrium of about half H3O plus ions and about half OH minus ions. The H3O plus is reduced as the sodium metal is oxidized. The exchanged electron goes to an H3O plus ion, kicks off two hydrogens as a molecule of hydrogen gas, and leaves a new OH minus ion sitting in solution. This raises the pH of the water as the concentration of OH minus increases. So let's look at the activity series again. Because I'm trying to get a more exciting reaction, I'll use metals that fall below sodium. I don't want to do too much work, so I'll use the stock solutions of 0.1 molar magnesium sulfate, manganese sulfate, cobalt chloride, copper sulfate, and hydrochloric acid that I already have in stock. In addition, I'm going to make a solution of iron 2 sulfate fresh because it doesn't store well. And since I already made it a couple of months ago and never did the experiment, I now have a solution of iron 2,3 sulfate because it's partially oxidized. But now we have to talk about that exception I mentioned. Remember that there's an increase in OH- concentration that accompanies the reaction between sodium and water. Each of the ions I'll be testing, with the exception of hydrochloric acid, forms an insoluble hydroxide, and there's a real good chance that those metals will not precipitate out as metals. We'll have to see though. That's what makes this legitimate science. So now that I have nice weather, a background soundtrack of Independence Day fireworks, and an alternative camera angle, plus the added bonus of a small family audience, we're ready to do some exciting experimental chemistry. I have no idea how this is going to turn out, so I'm excited. First, we'll do the reaction between sodium and distilled water. This will be our baseline. The first experiment will be using magnesium sulfate. This is the closest in reactivity to sodium, so I went into this suspecting that the reaction would be the same as water or even a bit less violent. If that suspicion turns out to be true, my lithium metal and potassium solution dreams will be shattered. Let's see. Interesting, that was less violent. That was less violent. And it didn't react all the way. While my audience enjoyed the reaction, it did seem to progress more slowly than the reaction with plain water. But you gotta love watching molten sodium burn. Also notice that there is a precipitate of magnesium hydroxide that forms in this reaction. Next on the list is manganese. Now, if the hypothesis is correct, this should have been a more exciting reaction. However, it was a little bit less exciting. That could be explained by having used a smaller piece of sodium than I had been using. And I suppose that's where my legitimate science argument starts to break down. But that's okay. We can still see that we're getting the hydroxide rather than the metal, and that is a valuable piece of information. As for the rest of it, we'll just call this a proof of concept test. And the next trial in that test will be an iron 2 sulfate solution that I mixed up this morning. Now this solution does have a very, very small amount of sulfuric acid in it, just as a stabilizer. When I first tried this idea, back in 2012, I used iron 2 sulfate solution. At that time, I performed the experiment in a 250 milliliter graduated cylinder, capped, stupidly, with a petri dish. This trapped the hydrogen inside, and it blew up about 4 or 5 times. That experience should have made me think twice before I capped the flask this past January. At any rate, I planned on doing the experiments that I'm doing now back in April, so I mixed an iron sulfate solution then. Even though I added sulfuric acid to stabilize it, it's still been oxidized over the past couple of months. So now it's a mixed solution of iron 2 and probably mostly iron 3. May as well use it anyway and see if the further oxidized iron actually makes for a more exciting reaction. Well, it does seem like iron 3 is a bit more exciting than iron 2, so that's an interesting observation. It's also interesting to note that the precipitate is different color in this example than the first, indicating that it is indeed iron 3 rather than iron 2. Since I'm not sure what the ratio of 2 to 3 is, in a future experiment I might try just a solution of iron 3 chloride so that I know it's all iron 3. Cobalt is next on the list, but since I have to treat cobalt waste separately from everything else, I'm going to hold off and do that at the end. Instead, I'll skip ahead to the hydrochloric acid. Magnesium and aluminum don't react with water, but both will react with hydrochloric acid. So will all the other metals that appear above H+ on the list, actually. The assumption is that the reaction between water-reactive metals and an acid will be more violent than a reaction with a plain water. As with our other solutions, this is only 0.1 molar HCl, so it's not very concentrated. That was indeed spectacular. There were streamers of burning sodium that shot up out of the beaker, and they went really high. In slow motion, you can see when they're ejected. It was first time luck though. Repeated attempts to get a wider angle shot failed. You'll have to take my word for it. But here's that slow motion. Look at that. That's how a chemist does Independence Day.
Oh, come on!
Next up is copper 2. This is the least reactive metal on my list, so theoretically, now that we've seen how this goes, this should be the most exciting reaction. Let's see.
Jesus! That was a good one. Jesus!
That was a good one indeed. My aunt was sure surprised. It was so good that I immediately threw in another chunk of sodium. In the meantime, though, look at how much liquid was ejected out of that thing. It's like a river of copper sulfate just flowing off the end of the table. Okay, here's the second one. Unfortunately, though, the second one wasn't nearly as fun as the first one. Okay, let's go back to cobalt. It has some pretty big shoes to fill now, but we'll see what happens.
Ooh, now that's cool. Oh, yeah.
This was overall a really nice looking reaction. First you had the streamers of molten sodium burning all over the place again, and then you had the juxtaposition of a dark blue precipitate in a light pink liquid. It was very pretty, and it added a whole other artistic dimension to this reaction. Since it was the last reaction, it was worth doing again. And it's interesting because every time I did two in the same solution, the second one was kind of a dud.
That was adorable.
Speaking of art, I had planned on using this board to repair a broken vinyl door panel, but I might rethink that. So let's summarize the experiment. We could see a definite progression in the intensity of the reaction as the difference in reactivity became greater. Some of them made pretty solutions, others were pretty gross looking. All of the reactions were entertaining, but a few stood out above the rest. At this point, I was done with filming, but in the time it took to start editing, I had a chance to reflect on the experiment. I had to know what would happen if sodium was placed in solutions of metal ions that are more reactive than sodium. Will there be a reaction at all? I think there'd have to be because there's still water, but would having less reactive metal ions in solution dampen the reaction or slow it down? Same as the first group, I'm going to use materials I already have in stock. I have a 0.1 molar calcium chloride solution already, so I'll use that. I also have lithium chloride, so I'll mix up a solution of that, and just for fun, I'll try a solution of sodium chloride. Lucky for me, I haven't even bothered trying to clean up the beaker yet. First up is calcium. I'm flying completely blind here. I have no idea what's going to happen, but this is as close to reactive as sodium as magnesium is, just on the other side. So let's see what happens. Interesting. That was considerably slower. The pop was still big too, but a little less convincing. What's also important to note here is that we got the calcium hydroxide precipitate, so there was some kind of reaction with the calcium ions. Next is a real curiosity, a solution of sodium chloride. My question here is, will Le Chatelier's principle apply? I don't know. Let's just dump it in and see what happens. That was really interesting. It lasted longer. It popped twice instead of once. And what I've noticed in both of these is that when I put the sodium in initially, the reaction is delayed. In the other one, sometimes it was almost instantaneous. In these, I throw it in there and it waits a second before it starts to react. So there's definitely a difference, and this is a really interesting experiment. Now the last one I'm going to try is lithium chloride. Now copper was the least reactive metal that I had in solution available to me right now. Lithium chloride is the most reactive metal ion that I have available to me. So it'll be interesting to see. If the trend continues, this would be a really sleepy reaction. So let's see. Well, maybe sleepy wasn't the word for it. It was slower than the other ones, but faster than sodium. So that's interesting. I'm not sure what this means for throwing lithium in a solution of potassium or even sodium, but I've got a lot to think about. There are a few other things I'd like to try with this concept, such as different concentrations of solutions or different metals, things like that. I'm also curious if the anion makes a difference. Like with the aluminum and copper example, it has to have chloride. So even if I keep everything 0.1 molar, would there be a difference between, say, chloride and sulfate? Not to mention the relative number of cations to anions depending on the charge of the anion. There are still other experiments I'd like to try with this that I don't have the materials for right now, so I'll definitely revisit this at some point in the future. In the meantime though, thanks a lot for watching, and I'll see you next time.
What a mess.